I'm gonna put a soup.
All right, here we go. We're going to talk about antennas, lines, and Smith charts.
Oh, I saw that.
Okay. This is not the one I want to start with. Let's try this again. Let's try number one. So we talk about some basic antenna parameters, a little bit about radiation resistance, gain, beam width, and antenna efficiency, ERP. Then we'll talk about standard dipole antenna, which is the basic form of almost all antennas. A little bit about verticals, random wire, and then they stuck in Fresnel zone, which you probably never heard of. I hadn't heard of it until.
Hey, Robert, somebody still has two devices unmuted, and it's causing people online a feedback loop.
Well, I guess if everybody turns their mic, unless they need to talk, there's a way to fix it. Is it still there? And there's some pretty pictures of different types of antennas. Your typical Yagi. This is, I guess you'd call that a stacked spiral.
So that's circular polarization?
No.
It's like a loop of that.
It's just a loop with.
Is that a multi-band?
Not necessarily, unless it can pick up harmonics. There's a magnetic loop and your standard J-pole and a typical vertical. And one of the things we always talk about as a reference is the isotropic radiator, which is the theoretical antenna that's a point source that radiates in all directions. So it's a perfect spherical radiation pattern in free space. I guess this doesn't matter where it is since you can't make one. It's theoretical. They say that its gain is 0, which means 1, okay, in any direction. 0 dB is 1. Right. And when we talk about gain, antennas don't actually have gain. Power ins, power out, maybe. You won't get more, you probably get less. So when we talk about gain, referring to an antenna, it's the amount of power in a particular direction if it's directional. But the total power on the surface of the radiation pattern is still going to be the same. If you put 100 watts in, there's 100 watts out, but if it's 100 watts in a very narrow lobe in one direction, then, that's effectively more power than if you had an omnidirectional antenna. And that's all a directional antenna does is concentrate the power in a particular direction.
So saying that your antenna has so many dBs of gain.
In a direction.
Yeah. In a particular direction.
Right.
Is that what you see is dB over isotropic?
Yeah,
It says DBI.
dBi refers to dB relative to an isotropic. dBd is relative to a dipole.
Okay.
And a dipole is 2.15 dBi. They always say it was 3, but it's really 2.15 in theory. But
Ideal.
yeah, since you can't make an isotropic, it's theoretical. So
It's all smoke and mirrors anyway.
a little bit. So what's an isotropic antenna?
Something roughly it's going to be Charles. What source?
I like Charlie. Okay, so another factor is feed point impedance. Because the antenna, depending on all kinds of factors, how high it is, what type of antenna it is, the configuration of the elements, like if it's a dipole, it not only changes with height, it changes as you change the angle of the elements themselves. As you lower them, it can increase the impedance of the antenna.
And we can talk about the.
Or decrease it depending on-
You're talking about the feed point impedance, right?
Mm-hmm.
Okay.
And that's where your feed line connects to it. So you want that to match your feed line. And normally you're going to use a 50 ohm feed line because your transmitter is, unless you really have something weird, it's going to be 50 ohms. Or you're driving it with twin lead or ladder line, one of those, which is higher impedance. Normally you don't have that on the back of a transmitter, but antenna tuners, sometimes, particularly the older ones, have outputs for ladder line and random wire. And the one thing that's not on here that I don't know if you ever watched any of Dave Kassler's videos, when he talks about antennas, everything affects everything.
Yeah.
And that's true. So a half-wave dipole at the optimum height, which is half a wavelength above the ground, is approximately 72 ohms. It changes as you lower it or if you tilt the elements either up or down, kind of has the same effect. At least I tried modeling and it looked the same. So which of the following factors affect the feed point impedance of an antenna? Bravo.
Bravo, yeah.
Okay, polarization is another parameter, and it's called the orientation of the E field or the electric field of the wave with respect to the surface of the Earth. And if the E field is oscillating horizontally, then it's horizontally polarized. If it's oscillating vertically, it's vertically polarized. So a typical horizontal dipole antenna will be horizontally polarized, even though its pattern, is basically a hemisphere, but it's still horizontal to the surface of the Earth. If I rotate it 90 degrees and make it vertical, it's now vertically polarized. Same antenna. And when we talk about verticals, the standard vertical, a quarter wave, is vertically polarized. It can't really make use of what we call ground waves, where it's a reflection off of the Earth. because most of the energy that isn't reflected is absorbed because of the polarization. If it's a horizontal, that ground wave is reflected, and this all depends on the soil conductivity. But the higher the conductivity, the more it reflects. So you can make use of ground wave on a horizontal where you really can't on a vertical. That's one of the basic differences. And ground wave is just a reflection that comes back in a certain point. It's additive to your signal. They combine at some point in the far field.
That was in phase.
No, but at a certain point they will be because the path length is different. It's kind of, when we talk about Yagis, it's a similar thing. That's what all those elements are doing. They're different phases and spacing. So at certain points, they all wind up in phase with the original signal. So which of the following is an advantage of horizontally polarized as compared to vertically polarized HF antenna?
Read that thing on the handle there.
This?
Some of the words are getting blocked in.
Alpha. Very good. Okay, ERP or effective radiated power. Basically, we figure out the gain, quote, of the antenna minus the losses, because you're going to have loss in the feed line, and multiply that times the power in. So it gives you the effective radiated power. So if you got 100 watts in and your antenna had a gain of 10, then you have a kilowatt effectively. If you had 10 dB, right? That's a factor of 10. If my dB calculator is right. Of course, you could have several dB loss in the transmission line and the matching. So, and 10 dB antenna means it's probably a Yagi or some beam antenna in order to get that much gain out of it. So an example here, we've got a 150 watt transmitter. We have 2 dB of feed line loss, which depending on the band isn't unusual. If we were at like 6 meter band, you had 50 or 100 feet of cable, that's probably at least that much loss. And you got a duplexer in the line, and you got a 7 dB antenna, and you add all those up and figure out what the multiplication factor is, because we come out with 2.8 dB. So what is that? You take 10 to the 2.8 divided by 10. Because remember the formula for dB is 10 log a ratio power. So in order to do the anti-log, you have to divide whatever that is by 10. Right, 2.8 divided by 10. Because you multiplied the log by 10 to get dB. So when you want to find what the ratio is, you have to divide by 10. This is where you need a calculator. I'm sure it will. You just have to figure out how. So in this example, we came out with 286 watts. We had 150 in. We take into account the gains and losses, and we have 286 effective radiated power in whatever direction that maximum gain is.
Now, would that be,
I mean, you could have almost zero power in the opposite direction.
right? So, or would that be essentially saying it would be the same as this ideal dipole with 286 watts feeding it?
Yeah. Yeah. So what term describes output taking into account all gains and losses?
Oh.
That's a hard one. That shouldn't even be on the extra exam.
Is it?
Yeah,
Oh,
that's a gimme. What's the effective radiated power relative to a dipole of a repeater with 150 watts power output, 2 dB feed line loss, 2.2 duplexer loss, and 7 dB of gain? You need your calculator.
No, I just need to remember the previous slide.
Yeah, but you know, in 5 weeks, you won't remember that.
Oh, yes, I will.
Okay.
If that's the one on the test, I'll get that one.
All right. Which one is it?
Yeah.
Okay. What's the effective radiated power of a repeater with 200 watts, 4 dB of feed line loss, 3.2 dB of duplexer loss, 0.8 dB of circulator loss, and 10 dB of antenna gain? Isn't that unusual for a repeater to have a antenna with gain? Aren't they usually vertical?
Oh, ours game.
It does? What kind of antenna is it?
What do they call them? It's, those little loop things on the,
Oh, I think I know the one you're talking about that's got all those little
yeah,
like handles.
yeah.
Yeah, okay. So did you come up with a 2 dB of gain?
Yeah.
Okay. So now how do you convert that to multiplying number?
I'd toss a coin.
Okay.
Uh,
Well, remember 3 dB is
what-
2. Okay. So it's less than 2.
Yeah. So it's gotta be alpha or delta.
And 1 dB turns out to be 20%. 0.2.
Hmm.
So I could assume that 2 dB might be what, up around a half or something? Well, let's see.
I'm thinking it's delta, just.
Think it's delta?
It's either delta or alpha.
Yeah, this is actually one of the very few where there's 2 answers very close together. One of them's right and one of them's not.
Yeah, I know, that's, they needed to throw one of those way out there. Ah! Okay, what is it,
So it's 1.58,
2.
Right.
So how?
10 to the 0.2. Well, you should have 10 to a power. And you normally you would put the power in and then do the 10 to the power button.
Oh, there it is. Yeah.
It's a little bit of reverse Polish.
I can't do that. Wow.
Yeah.
I gotta figure out how to do this thing.
All right. Oh, here's another chance.
Oh,
We got 200 watts, 2 dB of feed line loss, 2.8 duplexer, 1.2 circulator loss, and 7 dBi antenna gain.
oh, same thing.
I came up
Alpha.
with 1 dB. Is that what you got?
Yeah. And I didn't do, I'm gonna stay at it.
Well, 2 and 2.8 is 4.8.
1.2, oh, that's 4.
6.
That's
Right?
2.
Huh?
2.
4.8 and 1.2,
Oh, that's 6.
5.8 and plus the 0.2.
Let me recalculate.
Well, I'm gonna pick the answer here.
Yeah, you do that.
All right.
It's still wrong.
It was 1.25.
Five times 10 to the 19th.
I think you did something wrong. All right. So there's 3 of those, so odds are good. You might get one. One of the other parameters you mentioned earlier was radiation resistance. And it's one of the definitions is it's a value of a resistance that would dissipate the same amount of power as that radiated from an antenna. So in other words, if your antenna is actually radiating 100 watts, then whatever resistance that calculates out is going to be your radiation resistance. So you know the current going in or the voltage on the antenna, and you actually have to somehow measure the amount of radiated power. Then you can figure out what the radiation resistance is. So it will look like a pure resistance. And you have that in the sum of the ohmic resistance because there's some real resistance loss in the antenna itself, depending on what the material is, especially if it's aluminum. It's not as good a conductor as copper or silver. So the feed point impedance will wind up being the sum of the radiation resistance plus the ohmic resistance. So if you know the radiation resistance and the ohmic, okay, you can figure out what the efficiency is. So it's just going to be the ratio of the radiation resistance to the total resistance. So it's radiation divided by radiation plus ohmic. So, right, unless ohmic was 0, and then it'd be 1. Can't be more than 100% efficient. It's also this ratio of radiated power to input power. But then again, you have to be able to measure the radiated power. And just because you put a watt meter in line with the feed line going to the antenna, it doesn't tell you how much is actually being radiated.
So how do you measure?
I don't know,
Okay.
but oh, Sherrod is here. So what is antenna efficiency? Brevard. Okay. See, a lot of people, don't like vertical antennas, because they're not very efficient. The biggest problem with vertical is the radial system or ground radials. If you've ever looked at broadcast transmission, which is where the radial system kind of got developed, and this wives' tale about quarter wavelength for the radials, that's not really true. It turns out because they had lots of money, they did a pattern of radials where the spacing at the end of the radial was 0.05 wavelengths apart. So however many radials it took, okay, to do that big circle, it turns out that at 0.05 wavelength spacing at the ends, they're approximately a quarter wave long. But it wasn't because they were quarter wave, it's because they decided to make them 0.05 wavelengths apart.
Why that? Instead of.
Some engineer picked it because, it's a cost trade-off. I mean, you could put a solid copper plate down, be kind of expensive. And for broadcast, we're talking long radials. So,
At Clark Field in the Philippines, they had a huge antenna field out there. And it was basically copper wire, the whole field. It was a grid of copper wire. And the Hucks would come and steal it. So what did they do? They powered them.
oh,
Didn't take long to find out who was doing it.
yeah,
They
okay.
were sitting right where they were.
So if you've got a quarter wave vertical and you got a good radial system or very good soil conductivity, or you happen to be on a boat,
Salt water's pretty good.
salt water is probably the best.
How about these people that advertise their verticals that don't need a ground plane?
Well, they work. I have one.
I had one. Yes. That could or could not, or could, or you could not. use
Well,
ground.
The one thing about the one I have, I can tune from 160 to 6 and be without a tuner less than 3 SWR. But, I wouldn't say it has any real gain, but it's very broadband. And when we talk about broadband, the bandwidth, one of the definitions is the frequency range over which the antenna satisfies a performance requirement. Typically, they talk about an SWR of 2 to 1 or less. So whatever frequency range you can do with under 2 to 1, is they call the bandwidth for that antenna, meeting that performance requirement. It's just an arbitrary number, but in most cases, 2 to 1 is a decent match. It means that you're, 100 ohms instead of 50, or 25 instead of 50. So reflection is not too bad. And you can definitely match it with most transceivers have a built-in tuner, and they'll usually go 3 to 1 unless they're in emergency mode. and then they can go 10-1. 7300 will do 10-1 in emergency mode. Half power. Or less.
Three of them staff power.
No, it starts cutting back at 3-1.
Yeah, I think, yeah. 3-1.
It'll do 3-1. So which of the following improves the efficiency of a ground-mounted quarter-wave vertical antenna?
$30 a wire.
I think we'll go with Cal.
Think we'll go with alpha?
Yes.
Okay.
The other is fine.
Which of the following determines ground losses for a ground-mounted vertical antenna operating on HF? Okay, talk more about antenna gain. Since antennas are passive, they don't really have gain, like I mentioned. Power out is equal or less than power in, and it's normally less than power in. So the definition of gain is the ratio of the radiated signal strength in the direction of maximum radiation to that of a reference antenna, either an isotropic or a dipole. So we do it as dBi or dBd, and you'll see them both ways. A lot of times they use dBi because it's a bigger number. It's dBd plus 2.15. So marketing likes bigger numbers. Let's see, antenna height. Okay. Half a wavelength turns out to be optimum as far as takeoff angle and I guess maximum power into the lobes, because usually at half a wavelength, you just have single lobes. As you get higher, you start forming multiple lobes going up. The takeoff angle might actually decrease, but you got more lobes and they all are consuming power. So you have less power in the main lobe. The trade-off is takeoff angle is slightly lower. And if it's got a little defect there. If it's a horizontal dipole, then you can use ground reflections also that we talked about. And that's called ground gain, which can effectively boost the signal, because normally that part of the pattern that's going to ground would be, especially on the vertical, is going to be lost, where if part of it's reflected back up and it's additive at some point, then that's an increase in effective power. This is kind of shown in the opposite direction, but an aircraft transmitter, looking at the glide slope antenna and how the ground effect works in that case, where you have this image antenna when it's a vertical, because it's really a dipole and half of it is below the ground. And that's the part that normally doesn't radiate unless you put radials out, which now means that bottom element of that dipole is now horizontal. It's not this way. So it doesn't radiate, but it can reflect. So what does the term ground gain mean? Violence. Delta sounds good. Okay, so pretty, right? Typical half-wave dipole. And the green line is the E field. So you see it oscillating horizontal to the plane of the Earth. Means it's horizontally polarized. And the red is the voltage on the elements, and you can see how it relates to the current generating the E field. And typically the half-wave dipole is 72 ohms when it's half a wavelength high. And the elements are horizontal.
And that resistance changes, or impedance changes because of the.
Height, angle, and something's next to it.
And all that stuff.
Right. You put another dipole right up by it, it's going to affect it. So we mentioned that it's the 2.15 dB relative to the isotropic. I guess that's the main thing on there. It's basically 2 dB more than the theoretical antenna. To calculate the length of the elements for a dipole, you can use the formula of lambdas equal to 0.95. They're assuming a velocity factor of 0.95, as if it was like a copper wire antenna, uninsulated. And that's a pretty good approximation. Times the speed of light divided by the frequency. So it's the old lambda equals 300 divided by f in megahertz, and then they threw in the velocity factor. Which means its electrical length is going to be more than its physical length. Example here is we have a 7.15 megahertz signal, and if we do the formula for doing it in feet, okay, this is where the 468 comes from. If you do the conversion of speed of light in meters to feet, you come out with that 468 number for a half wave dipole. So it says it's 65 and approximately half feet. We're at 20 meters, it's going to be 33 feet. So what's the approximate length for a half wave dipole cut for 3.550 megahertz? Well, since it was 65 feet at 40, what do you think it's going to be at 80?
What?
65 feet at 40.
What's that?
468.
468.
Just remember 468.
Sometimes they use 469. And I believe that has velocity factor in it.
Yeah. I think it's 492. Take it out.
Did you get the right answer?
Oh, no. I didn't, so let me see why. I got it when I put the right numbers in.
That helps.
It's count issue, no.
Well, here's another one.
You do that?
So 14.250, if we're going back to 20 meters. So you probably don't need the calculator. In fact, you should know that
I
number.
know, but I want to calculate.
Okay.
Exercise knowledge.
Okay. So how much gain does an antenna have compared to a half wavelength dipole if it has 6 dB gain over an isotropic radiator? What do we know about the difference between a half wave dipole and isotropic? 1.5. So what do you do with that number?
Oh,
Very good.
yes.
Now you work that out in your head.
No, I didn't.
Oh. Radiation pattern for a dipole. In free space, it's going to be a figure 8 at right angles to the antenna. Actually, I didn't have a picture of the real figure 8. When it's at the optimum half wavelength height, then you get a figure here of kind of a figure 8. And you can see if you look at the vertical cross section, those lobes, okay, are what give you the takeoff angle. So as you raise that, those are going to come down, but then you're going to start getting additional lobes. And the size of that primary lobe is going to be smaller. When we get down closer to the ground, then it starts to become essentially omnidirectional. And if you get down below 1/10, which we'll talk about later, it becomes invis, near vertical
vertical incidence scattering.
incident scattering. So, and it's like this. Well, it's very important. Military uses the hell out of it. It allows you to get over a mountain at short distances, a few hundred miles. If you're doing propagation, you can't talk to somebody 200 miles away. You're going to bounce right over them. You can with Invis. You see a lot of military vehicles, and there's a loop looking thing like handlebars. That's a loop antenna that's horizontal. That's an Invis antenna because it's just basically going straight up.
So let's say we're at a park, doing a club gathering and somebody takes their antenna and lays it along the rail of the boardwalk and transmits from it and catches somebody 3 miles down the river. So is there a way to tell if it's in this, okay, because it's so low, or ground wave? Because I would think that close it would be ground wave. I would think the first 30 miles would be a ground wave. And then anything between 30 miles and your first hop would probably be in this.
I don't know. I guess could be either. Just like sometimes you can't tell whether you got a long path or short path. If you ever seen any of the YouTubes by Raisa, what is she?
I think
R1BIG, I believe they're called.
Well, I think she might have recently changed her call sign.
Oh, it could be. She's a little Russian
Oh,
girl,
yeah.
little blonde,
Blonde-haired Russian
that
girl.
does lots of YouTubes. And one of the ones she did, well, actually a couple like that. She laid a dipole out on the ice of a frozen lake and made contacts with it. So I'm assuming that was basically Invis. She also buried one on the beach and did it too.
I think I didn't watch the whole thing, but I think that got my answers. I started watching. But yeah, something on a beach.
Yeah.
Or buried, she buried.
Right.
everything.
Yeah. So is that Indus and saltwater, all the above? So what's the radiation pattern of a dipole in free space in a plane containing the conductor? They threw that in to be confusing. Well, your radiation pattern is 3D, so a plane is just going to slice through it. So they didn't say what the plane was. Let's assume it's horizontal. The old figure eight at right angles.
So, you know,
Oh, remember if you put your horizontal dipole up north-south, okay, your pattern is east-west.
oh, that's what they mean.
Yeah.
Okay.
So how does antenna height affect the azimuthal, that's the horizontal, radiation pattern of the horizontal dipole at elevation angles higher than about 45 degrees? I had trouble understanding that one because throw in the 45-degree elevation angle in there. It will be clear when you see the answer, I think. Well, we can throw B out, right?
Yeah. Gonna have to go with Charlie, and you can put a D out.
Yep. You can throw D out.
Back to Charlie.
So you're Alpha and Charlie, right? So I would go with Charlie. And if you look down here, where this red dot is, that's 45-degree angle. If you sliced it at that point, you're going to see that almost circular pattern. They just threw that in to confuse you so that you'd miss one.
See. It is.
Okay, in dipole impedance, like I said, it's approximately 72 ohms. This says it's actually 73 plus J 42.5 because there's some reactance, which means wherever they measured that, it's obviously not at resonance. Because if it was resonant, the J term would be 0, right? You'd have no inductive or reactive component. But this is measured at a half wavelength. So maybe that's the reason why there's some inductive reactance. It may go away if it's in free space, So as you, if you look at this plot, it's based on soil conductivity. So the red line is very poor soil, like Colorado. Rocks, not.
The words in our saying,
Our sand is wet.
I say it's not.
How far did you dig down?
Yeah.
You don't have to go very far.
Oh,
Down about 2 feet, yeah, get your well going.
We don't have the best, but it's better than Colorado. The green line is a very good ground, or excuse me, average ground. And then the blue is very good. So you can see, and they're plotting the resistance. So it gets up, we're at what? 26 meters. We're 92, 93 ohms. And this was a 80-meter dipole, so they don't actually not even showing the height at a half a wavelength, which is off the chart. But a quarter wavelength, we're down to about 85 ohms. And it doesn't make too much difference about the soil at those points where it crosses over. But as you start getting closer and closer to the ground, so you get down here at 10, which would be a quarter wavelength, right? I mean, not a quarter, eighth of a wavelength. You're down just a little above 40 ohms for good soil. Doesn't change as much on the poor soil. Not as much as the blue line. The blue line is very good soil. So it has a bigger variation.
So if you've got really good soil
Mm-hmm.
and you want 50 ohms,
Yeah,
okay, so you're gonna have to.
but you also want to optimize the pattern, so there's always trade-offs. Do you want to get
Well,
50
this-
ohms or you don't want to have the best pattern?
So you have to decide, do you want a good match or do you want a nice pattern?
Right. But you can always use some matching technique, okay, with whatever it is, because it's kind of a special case when it's 50 ohms. It's pretty low to the ground. Or you've dropped the elements at 45 degrees.
Are we gonna talk about in-field dipole?
Mm-hmm. And off center fed and center fed and ZEPs
What?
and ZEPs and double ZEPs
That was it?
from the Zeppelin, Graf Zeppelin. It's the antenna that they used was the end-fed half wave.
Well,
We get there.
there's no ground for it.
Okay. Basically, you can see that the resistance goes down, okay, depending on height. And you can't tell from this chart, but as you move towards the end, as opposed to being center fed, the resistance increases. So when you get all the way to the end where it's an end fed, you have the highest resistance, anywhere from, I think the chart coming up says like 5,000 ohms. I think it's more like 2,500, 3,000, but definitely kiloohms. Where off center fed, depending on whether it's quarter or 30%, is like 400, 200, 400 ohms. But we'll get there. Okay, so a center fed is approximately 72. It's a decent match with a 50 ohm cable without a tuner. It's less than 2-to-1 SWR. And if you had 75 ohm cable, it's almost a perfect match. If you go with off-center fed, it's about 200 ohms. And I think that's for when it's 25%. At 33%, I think it's closer to 400. And then they're saying in-fed is about 5,000. I don't think in practice it's quite that high, but it's very high.
Is that a measurable resistance or is it
Yeah.
just calculated?
You stick your nano VNA on it, and it'll tell you what it is. It'll give you R plus R minus J. And it'll also give you just the magnitude, which is the vector value. How does the feed point impedance of a horizontal half-wave dipole change as the antenna height is reduced to 1/10 wavelength above ground? How's the feed point impedance of a half-wave dipole change as the feed point is moved from the center towards the ends? Okay, vertical antennas. The second most popular. Because almost every other antenna is basically a dipole of some sort. One advantage is it has a very small footprint, except for your radio pattern. But other than the radio pattern on the ground, you don't need much area around it. It has a lower takeoff angle typically, but it tends to be more omnidirectional. I should say it is omnidirectional, unless something else is close by interfering with the pattern. And like if you put two of them up, then you change the pattern considerably, and we'll talk about that in a bit, called phasing. The formula for calculating the length of the element for a quarter wave vertical is 234 divided by the frequency. Almost sounds like 468 divided by 2, doesn't it?
This is above, huh?
What I'm saying.
Okay, so it's essentially a vertical dipole, okay, where half of it is your ground plane. And the radials that you use can either be buried or just laying on the surface. Apparently, it doesn't make much difference, except if they're laying on the surface, then lawnmowers and people and stuff. So usually people either bury them or staple them down.
It's laying on service to be temporary.
Which of the following best describes the radiation pattern of a quarter wave ground plane vertical antenna? What's the, oops, I double clicked.
Okay.
Double check.
Yeah, I'm gonna have to get a new mouse. Everybody got that one?
Cable, that may not be a good bit, you gotta.
Where should the radio wires of a ground-mounted vertical antenna system be placed? Charlie. Impedance of a vertical. They say it's approximately 35 ohms when you have horizontal radials. If you slope the radials, because a lot of times you can have a vertical mounted on a pole with radials. I have a VHF UHF that's like that. It's up at 25 feet and it's got little 2 or 3 foot radials. If you change the angle of those, you can affect the feed point impedance. Just like changing the angle of your dipole elements. You know, a inverted V is essentially that. Which of the following is a common way to adjust the feed point impedance of a quarter wave ground plane vertical antenna to be approximately 50 ohms?
Wait. Oh,
I'm pretty sure when I modeled it, something like that, doing them up did the same thing, but I'm not going to challenge it. Oops. Okay, random wire is just a very long piece of wire, usually multiple wavelengths long, where you attach one end to a tree or pole or something, and the other end goes straight into the shack, into your antenna tuner or your transmitter. Now, what kind of problem could that cause? You're putting out a kilowatt. Well, random wire probably wouldn't handle it. Well, I guess you have big wire. And part of that wire is in your station.
you probably don't want that.
Well, you probably don't want to be
And you don't.
high power transmitting. Okay. Because it can cause one of those RF burns that fortunately I haven't had. People tell me it's no fun. Goes right to the bone. What's a characteristic of a random wire HF antenna connected directly to the transmitter?
Bikini.
Okay, Fresnel zone. When you're doing a point-to-point communication system, and this is typically at UHF and above frequencies, you have this radiation pattern between two stations that's an ellipsoid. And the frequency determines the diameter of that ellipsoid. And they divide it up into different zones. So when they're designing a point-to-point link, you have to look for obstructions that interfere with that ellipsoid. So in this case, see, they're clear of this little hump in the middle. And they divide it up into like 3 or 4 zones. So the smallest diameter zone is going to be at the highest frequency. And as the frequency goes up, this ellipsoid gets flat, well, not flatter, but narrower. Okay.
What happens if it hits that mountain or wherever in the middle?
It interferes with the pattern. You lose part of the signal.
So you need that whole pattern to get the signal?
Well, yeah, because the receiver is receiving that and the transmitter, I mean, they're actually going across one another. Okay, but this is the ellipsoid is the result of what the transmitter and receiver are operating on. So the idea is to construct it, either get the ends high enough or high enough frequency that you're missing any of the obstructions in the middle. There's only one question. There's formulas for calculating the radius in meters and feet. If you're doing 1 gigahertz, the zone 1, which is the smallest zone in the center, is going to be 11 meters in diameter. If you're at 10 gigahertz, it's down to 3.5 meters. So you see it shrinks considerably depending on the frequency. So what frequency band has the smallest Fresnel? I think you pronounce it Fresnel zone. There you go. So we talked about isotropic radiators, feed point impedance. Depends on the height and also the length diameter ratio of the antenna elements. The length diameter ratio. Yes, as you change the diameter of the wire, you will affect the velocity factor. Remember that question that was a couple weeks back? If you increase the diameter of a conductor, what does it do to its electrical length? And I actually found the answer in the, I don't know if it was in the previous one, in the latest ARL handbook. There's a little paragraph about it, and it says kind of what I thought. The capacitance increases faster than the inductance. So it becomes more capacitive and changes the velocity factor. We talked about polarization, ERP, which is basically the power times the total system gain. Efficiency, which is radiation resistance divided by the total resistance. The bandwidth, typically they use 2:1 as the performance criteria. Gain is defined as the maximum directional power versus some reference antenna, dipole or isotropic. Ground gain was the increase in signal strength from a ground reflection, which helps a horizontal dipole. It doesn't help a vertical. The formula for the length on a half-wave dipole was 468 divided by the frequency in megahertz. The radiation pattern is a figure 8 at right angles to the antenna element. Impedance decreases as you get close to the ground. For a vertical, it's omnidirectional pattern. It's 468 divided by the frequency divided by 2, because it's a quarter wave instead of half wave. It's the same formula, just half of it. And the impedance of the vertical is 50 ohms if you have 45-degree radials. Otherwise, it's 35 ohms, assuming there's no matching transformer as part of it, which mine has, which is supposedly why it doesn't need radials. Random wire it's a non-resonant antenna with a very long wire that goes directly to the transmitter. So you can get a lot of RF. You really need to have every chassis tied together, single point ground. And the Fresnel zone was just an ellipsoid radiation pattern between 2 points. That's frequency dependent. Questions on those?